Okay, so today what we'll be taking a look at is the case when the external forces depend on the velocity of an object and understanding how these forces influence the motion of such objects, which we know we can grab if we use Newton's second law. So, in other words, we will now study the case when Newton's equations of motion look like this. So we have usual m times d by dt of a velocity term equals a force vector which depends on the velocity vector v. Okay, and here this will be some sort of resultant force. Resultant force depending on the velocity v. All right, so you may ask, well, where do you find such scenarios? So, and we'll get back to this later, but quickly, examples of such scenarios occur when objects move through a resistive medium. All right. Okay. Some examples include air, for instance, when you fall through the air, or a fluid like water. So you can experience some forces, for instance, when you're trying to wade through some fluid, or imagine you're at the swimming baths trying to wade through some water. Okay, and we'll discuss this example a bit later. So in particular, we would like to consider (1D) problems. Okay, now this just means the motion takes place in one direction. The motion of an object takes place in one direction. Okay, so in this case, what you have is you have your velocity, say v is vxi, say, for instance, consider motion in the x direction. Okay, so you have your velocity is vi, and then you have maybe a force which acts parallel to the x-axis. So you have something like this, which is just F, which is a function of V, X, multiplied by I. Okay. And then this allows you, as we have seen many times, this gives the equation Vx, the time derivative of Vx equals, multiplied by the mass of the object, equals F of Vx. Okay, and I may also later use the following notation. Use V to represent. Later, I may use V to represent the velocity where I drop the subscript. Okay, where the subscript is dropped. All right. Okay then, so, well, let's put this into practice. So let's just think about how we would solve. How do we solve such an equation? Okay, so this is the equation. I'll write this down again. So we have this m dv. Now I'm using v equals f of v. Well, you may already notice that this equation happens to be one which is separable. So a keen eye will spot this is a separable equation. Therefore, this is just one way in which we can solve this. So therefore, try integrating with respect to t after the following rearrangement. Okay, so we'll divide by f of v and by m through the equation. So then we get this. We get 1 over f of v dv by dt, and we'll take advantage of this approach later, and then we get this. Okay, so what happens next? Well, integrate with respect to t, and we get this integral on the left hand side, and this is an indefinite integral. Okay, so this is an indefinite integral, and so we have integral of 1 over m dt. Now this, by the chain rule, as we know, is dv by chain rule. So this gives the following. This integral to compute of a function of v with respect to v equals, and the right hand side is fairly easy to compute. That's t over m plus some unknown constant, arbitrary constant, as we know. Let me just reorganize this a second. There we go. As we know, we can get this using some initial conditions, found using initial conditions. And if you know how to do this, if we know how to compute this, because let's face it, we don't know what f of v is here. If we know how to compute this, we may be able to find v, to find the velocity v as a function of t. Okay, explicitly written as a function of t, just by rearrangement. All right then, so this is the sort of idea. Now, next, what we'll talk about is where these forces come from. So we'll look at the motion of objects through a resistive medium. Right, okay, so what we're interested in, we want to characterize the forces exerted on an object that moves through a fluid. Okay, and this fluid, a fluid's quite a general term, could refer to air or some liquid. Basically any medium that presents a resistive force to the motion. Okay, so that's the idea. Now, well, what about this? So, okay, so let's start with an example. Consider a body that moves through a fluid. All right, so to do this, the body must force the liquid or the fluid, let's say the fluid, more general, the fluid out of the way. So there is a sort of exertion of a force on the fluid, right? So it uses forces in order to do this. Likewise, by Newton's third law, each force has a equal and opposite reaction. So Newton's third law tells us, says the fluid exerts equal and opposite forces on the body. Okay, so this is important, equal and opposite forces, and effectively we're concerned with the resultant force applied by the fluid onto the body. Okay, I'm just underlying some principles which are important in this development. Okay, so we want to know, or we would like to understand the resultant force exerted on the body. That's the whole idea. That's the catch. Remember that remember that when we're using or when we're modeling dynamic problems, we need to know the resultant force that acts on a body in order to understand its motion. So when a body moves through a fluid in a similar way, what we're wanting to know is what do the external forces do? How do they combine to form a resultant force? And this force will include force exerted by the fluid on the object. And then with Newton's equation of motion, we can determine the motion of the object. Okay, so consider the following case. So that was the principle. So now we'll consider the following. So you might have some body, looks like this, moving through some medium. Okay, so here what I've drawn is an object in 2D. Object moving in 2D. So there might be some y displacement and some x displacement associated with this object. This is as we know, let's not forget that reference system is important. This is our reference system. It's not really important for this example, but this is just to remind you that whenever you're doing problems of this form, it's very important to write down your reference system so that you know how to calculate the force vectors and displacement, velocity, etc. Reference system. Define with respect to O. Okay, so this is our body. Let's see if I can try and colour this in a bit. So what happens is it may have some velocity, this body may have some velocity, and I've drawn, just to make it stand out, I've drawn quite a large arrow, but this arrow represents the direction of the velocity, okay, the direction in which the object moves. So this describes our vector v. All right, so what happens is, well, you experience resistive forces. You experience two of them. There are two forces, excuse me. So this is our fluid. And you experience the forces exerted by the fluid, which happen to be two kinds of forces. You experience a force that resists the motion in the direction that you're moving, called drag, characterized by some vector d, drag force. And mind you, let me do that in block capitals, drag force. And simultaneously, you experience another force due to the fluid, which is called, and this acts 90 degrees to your velocity. And this one is, sorry, this one we denote by L, which is the force vector that represents lift force. Put this in block capitals. So the resultant force of the fluid. Now, lift force, what does this do? Well, this is the thing that in fact, this is the thing that makes air travel possible. So, well, what about the resultant force? Well, the resultant force F is the sum of lift and drag forces. So we have the following formula. Let me convert back. So we have F, our resultant force, is equal to the drag force D plus, characterised by the vector D, plus the lift force L. Now, in most of the applications that we'll look at, in most applications, or in fact in all applications, this L will be 0. In all examples, this lift force is 0. Okay, so we'll only have F is equal to the drag force. But before we do this, so let's talk about the application of lift force. So let me write this down. So lift force is necessary for applications in air travel. Right, so to get rid of this lift force, what we'll assume, we will assume our body, and this is a fairly rigid assumption, but okay, it works for what we'll do. So our body is a body of revolution. That moves in the direction of its axis of symmetry or axis of revolution. So probably you're thinking, well, when is this applicable? Well, e.g. a cylinder. But you can think of more things, which well, maybe I even draw this example in a second. So you have here axis of symmetry, you have a line, and then when you rotate this around 360 degrees, so remember that the body of revolution is formed by some curve, and you rotate this around the axis of revolution, this curve, and what you end up with is a three-dimensional object. Now, this object will move in the direction of its axis of revolution. So this is parallel motion, parallel to this, the axis of revolution. Here's another example, not necessary for me to do this, but you might have something like this, another body of revolution. Something like this, moving through the medium. Okay. Right, so in these cases, in this case, L is the 0 vector, okay, which is just 0i plus 0j plus 0k. Now, couple more points, very interesting. So we wanted to know about the type of forces. So we wanted to know about the type of forces acting on the object. On our object moving through the liquid or the fluid. So what we've identified is we identified drag and lift forces. Okay. So, well, actually, the ability to understand what the form of these forces are is one of the greatest problems in hydrodynamics. So, in fact, as far as we have, so we still don't know the form of the forces. The form of the forces. Okay. This is it. Now it comes down to a problem of trying to find what the form of these forces are. So determining lift and drag forces is one of the great problems in hydrodynamics. Okay, so it's one of the great problems in hydrodynamics, and usually we find them by experiment. Now, okay, just a point to add. Coming back to here, what we're using is using symmetry. Of our body and the motion and type of motion to eliminate the force due to lift. To eliminate that lift. So this is zero using the symmetry of the body and the type of the motion, which is one-dimensional motion, to eliminate the lift. So, okay, if you wanted to know about the lift and the drag forces experienced by an object moving through a fluid, then you have no alternative than to do this tricky game, which is experimentation. Now, when we started all of this together, we looked at the concept of dimensional analysis. And using dimensional analysis, we were able to look at how we can simplify a problem that we were interested in. So remember that a problem may come packed full of all sorts of variables, and depending on which ones you deem relevant, using dimensional analysis and the Buckingham Pi theorem allows you to determine a formula which shows you what the most important parameters are in the problem, which these parameters involve dimensionless constants. So with this in mind, if we had to do an experiment, we can always remember from week 1 or topic 1 on dimensional analysis. We can determine or reduce our experimental effort in identifying the drag force, which is what we're interested in. We're not interested in the lift force, the drag force. Okay, And actually, you've already done this. So look at exercise sheet 1. Concerning example with the van moving in against wind. So, how do you do this? Well, the central result to do this, we do this using Buckingham Pi theorem. So, all's not lost. This does come in handy, especially when one has to do some modelling of physics. All right, so you get this. You can find such a force. And we did this when we looked at the van moving against the wind in exercise sheet 1. Okay, so in a similar way, we can calculate drag experienced by other objects. So, e.g. a sphere. So in this case, what would we do? Well, here's the example, and you can do this yourself using the notes related to dimensional analysis. So suppose we need to know the drag force acting on the sphere. Okay, this sphere has a sphere having radius A. Let's see. Okay, moving through a fluid. With velocity v. Or actually, let's reorganize this. So we have a sphere having radius a, moving through a fluid. Okay, moving through a fluid with, and then we'll list the properties of the fluid. Velocity v, density, okay, just a second. So this is the sphere that has the velocity v. All right, so then and this is the fluid density. So let's write this, the fluid density, rho, and a fluid having dynamic viscosity mu. Having dynamic viscosity u. Then what you can do is repeating similar steps. In topic 1, we can find the magnitude of the drag to be b, and then you have d is equal to rho A square V square F rho VA over mu. All right. And this is an unknown function. Unknown. Unknown function, and you have to determine it. Remember, you have to determine this experimentally. That's the aim of the game. So these are two dimensionless quantities. So, oh, sorry, this is a dimensionless quantity. Okay, this is a dimensionless quantity, and this is known as the Reynolds number. Okay. So, well, what about this? So, Reynolds number. Reynolds number R is the following. So this is R. It's rho VA over mu, where mu is the dynamic viscosity. And dynamic viscosity characterizes the resistance of your fluid to external forces. It can also be written as VA over nu, where this thing here, this is the kinematic viscosity, which is the internal resistance. It characterizes the internal resistance of your fluid to the action of gravity. So if you were to consider a fluid flow under the action of gravity, then this nu is a parameter used to characterize the type of flow you will probably encounter. Okay, so what about this? So R, here R characterizes the type of flow we can encounter. I.e., will lead us to knowing the drag force in various cases. Okay, so there are two cases. Two cases that we consider. So the first one is high Reynolds number. When this is very high, Reynolds number. And this is applicable to flows. For instance, high velocity streams. Okay, high velocity streams which have chaotic motion. Okay, chaotic motion, and this means you can have things like vortices, i.e. vortices, and other types of chaotic behavior in the flow. So just look at, for instance, water flowing down a river. Sometimes you see the water swirling around. If the velocity of the water in the river is sufficiently high, you'll see all sorts of strange, or not strange, but maybe things going on in the flow. Things like vortices, where the fluid will warp around a certain point, going around in a circle towards the centre and of this vortice, and you'll see other types of chaotic motion. Okay, so the second one corresponds to low Reynolds number. And you might consider this to be the case where you have slow-moving objects. In viscous or sticky liquids. Okay, so what about it? Well, high Reynolds number and you can think of maybe a range for R like this, or a sufficiently high Reynolds number. Let's say this. High Reynolds number, you might have some interval like this. And then it remains to find what is F. What is F of R? Remember that F of R is the following. Rho V A over R. Over R over mu. Well, experimentally, one can show it can be shown F of R is approximately constant. Call this constant C. Okay. So this means then, using our drag formula, so let me label this with a star. So we'll have a constant now coming in from here, and this means that the drag force experienced by our sphere is proportional to the square of its velocity. Okay, so in star, let's take this across to the next page. In star, this just means the following. It means the drag, D, is equal to some constant times rho A squared V squared. Okay, in other words, i.e., the drag is proportional to the square of the velocity. Drag force proportional to square of V. All right, and this is called the quadratic law of resistance when we're talking about drag forces. Okay. Now, at the other end, we have low Reynolds number. And again, this we can also find via experiment, and it's already been done for us. So low Reynolds number. So here, in low Reynolds number, here the quadratic law does not hold. Does not hold. And in fact, there was a British applied mathematician who determined the form of this force at low Reynolds number. Sometimes, and this particular flow, a fluid is referred to as Stokes flow. So Stokes and applied mathematician from Britain showed that our F, our capital F of R, is in fact proportional to 1 over R. Okay, so the function of the Reynolds number, F of R, is proportional to 1 over R. So this means that F of r is equal to some constant, which we would need to find experimentally. It depends on, that's a good point actually. So this constant depends on several factors, and should be determined, linked to the experiment. Okay, so it should be determined by experiment. So again, this is the C that we find again by experiment. So what happens? Well, let's insert in star. So we have D equals rho A square V square now multiplied by C over R. Remember that this Reynolds number is rho VA over mu. Okay, so this is C over rho VA over mu. Let me just double check. Okay, got that. So if you do some simplification, what you'll see is a velocity cancels in power 1, and you're left with the following. So you're left with C mu in the numerator, A V. Okay, and well, here D is proportional to V, and we call this the linear law of resistance. All right, so yeah, again, this you would find, or at least find C by experiment. But at low Reynolds number, what you will experience, or a body will experience, is if it's moving through a fluid, is a drag force which is proportional to its velocity. So what's the idea now? Well, now we've covered two different types of laws which bodies experience due to drag. Well, let's put it this way: forces that bodies experience due to drag when they move through fluids. These forces are characterized by two laws: a linear law of resistance and a quadratic law of resistance. There may be other scenarios where it's not linear or quadratic, but what we're going to do is we're going to use these two laws in subsequent examples to explore how to solve problems when we come back next time related to understanding how objects move when they experience forces which are velocity dependent. So that is everything for today. So I'll see you next time when we start looking at some examples.